Okay, so if you were struggling a little bit, then we said use some points as your guide. Remember, the parent function is literally the simplest thing that involves squaring. So a parent function means I just want you to do the math operation of whatever function we're studying. So if we're square rooting, we would just be square rooting. For absolute value, it's only absolute value, but nothing else involved. So with a quadratic, we're only squaring. So you should have got these key pieces of the parent function. So this should be how your parent function looks. Oh, you guys can't see it? Oh, man. Okay. They can see it on the recording. Too bad you guys can't see it. No, I'm just kidding. All right, there it is. Okay, so are we okay with the parent function? Yeah? Right, so you have to know your parent functions. If you ask me when we're doing homework graphs, like, how did you know to start with these numbers? I went and memorized my parent function. So when someone says quadratic, in my head immediately pops this picture of the parent function. I know where the vertex is. I know that if you go 1 unit to the left or the right, you go 1 unit up. And if you go 2 units to the left or the right, you go 4 units up. And I know this table or can quickly make this table because I understand what's supposed to be in it for the parent function. Okay? So that's kind of your expectation of what you're supposed to know. So a little bit of review, and you guys give me answers. We'll go through these here. And then we'll talk about the transformations. So the chart below, if it will move, but it won't move because we're having a rough technology day right now. There we go. All right, so the chart below this, what was our vertex for our parent function? 0, 0. All right, now different people can give me each one. Somebody tell me x-intercepts of this function. Cooper.
0, 0.
Okay, Cooper's not answering another one from here. Y-intercept. Okay, Katie's not answering another one from here. Domain. Jake? Good. And if you guys like interval notation for domain, that's negative infinity to infinity. Range for this graph. Andy? So almost, right? It does go up forever, but it does hit a minimum, right? You want to revise your answer? What's that? Perfect. So he said all real numbers greater than or equal to 0, since our range is talking about y values, we'll express it this way. Or if you like the interval notation, we're saying 0 is the smallest. It doesn't have a maximum. We reach 0. Infinity is more of an idea, so we don't exactly reach infinity. Somebody new, increasing interval. Yari. Good. Remember, we're not saying, it's a little confusing here because 0 makes you feel like we're talking about y coordinates, but that's really there because that's the x. So from 0 and x is beyond that, the graph is constantly behaving like an increasing thing. What about our decreasing interval, Jay?
Negative infinity from 0.
Perfect. Okay. Is this 1 to 1? No. Okay, it is a function, it is not 1 to 1. Okay, so now for rate of change, anything that's not linear actually does not have a consistent rate of change. For this parabola, when we move over one space from the vertex, we went up 1. But when you move over another space from the vertex, you go up 4 from where it originally was. It's not consistent. It keeps getting larger. In calculus, you'll learn more about how you can establish rates of changes at specific points. And actually, a whole bunch of your first quarter of calculus will be based on finding those rates of change, okay? What is our axis of symmetry? Someone that hasn't talked to us yet. Brody. Good. Minimum value. Someone new. Grace. Good. Maximum value. Connor. Good. And then asymptotes are not something for this function. So I'm sorry if it's annoying to you that you're like, why are these things in here? Because we wanted them to all look the same for you, so you understood every time you're looking for the same information. Okay? And now what we're going to go do is we're actually going to go do the algebra to trig version of the problem. So I'm going to be perfectly honest with you. Algebra 2 has this same paper. They have these same two exact things on the front. What they don't have is what's on the back of the paper. There's a back. Super exciting. Okay, so the boxes are not new mathematical functions. It's called sometimes the PDF when converted from Word doesn't print certain objects. So it didn't print the objects, so I wrote the equation above it in my very sloppy handwriting so that you can make sure you understood what was there. So this really is supposed to say f of x equals -2 as an a value. And then inside of your squaring function, you have a 1/3 x plus 1. And then outside of your squaring function is a +5. Is that okay with everybody? Sorry, we normally don't take a lot of time to write things down, but when you mess it up, you gotta let people have time to write it down, right? So here we go. All right, now our job is to graph this quadratic, okay? Now, just like with absolute value or with greatest integer function, plugging in is not necessarily the best way to graph this function. You will get part of the function. The problem is you need some key pieces to graph the quadratic correctly. You need to know where it turns around, right? You can't just randomly plug stuff in and make a guess. You need where it turns around, you need that axis of symmetry, and then you need some points on either side of it. So what we're gonna do is we're first going to kind of analyze this equation and practice our transformations from yesterday, okay? So if I want to know what all the transformations are here, like how the parent function became this, like what's happening to that basic one that we drew, I want to write down all the transformations, but first I have to change the equation a little bit, right? What's wrong with my equation? Why can't I see all the transformations directly right now? Maddie? Good. I don't want 1/3 x plus or minus something. I want the 1/3 to be separate as like the b value, and then I want a quantity that's just x minus h, so x plus or minus a number. So I'm going to keep everything the same except for inside of the squaring function. I want to separate the 1/3 from another quantity. So I'm always taking the b value right out. And when I say out, I'm not factoring it all the way out of the squaring, right? That would require a lot more mathematical operations, but just out of the quantity. And that will leave me with x. And what will it leave me with here? Instead of +1, what will I have? +3, okay? Because 3 times 1/3 is what would make the 1. If you're unsure of how to get that, you should be taking what was there originally, 1, and dividing it by what you factored out. So 1 divided by 1/3 would give me what's left in there as 3. Now I have everything in the right spot. And so when I identify what's here, I can see I should be able to see an a value, a b value, an h value, a k value. Is everybody okay with how I'm identifying those values? Like, are you okay with the fact that h is -3? And b is still 1/3. The value in the equation is 1/3, even though I'm going to interpret it differently. It doesn't change how the number looks in the equation. Okay? All right, so let's start with horizontal stuff. These things are horizontal because they were immediately affecting x before we would square anything. They were happening to x inside of the function. Okay? So the b of 1/3, can somebody say in words what type of transformation that's supposed to cause? Taylor?
Horizontal.
Okay, so horizontal because it's in there affecting x. And then do we want to say stretch or compression? Stretch. So it's 1/3, which might make us immediately want to say compression. But the way we use the 1/3 on the graph is different than the way the 1/3 shows up in the equation, right? In the equation, it's 1/3, but on the graph, how's it really going to be used? 3, okay? The reciprocal of it. So it's actually going to be a horizontal stretch, okay? And then you want to say by 3, or if you can write times 3 next to it. So if we were measuring how far things were from the y-axis, they're now going to be stretched out. So don't go change your graph here, but what I'm showing you guys is this point would stay because it's on the y-axis. This point used to be how far away from the y-axis? 1 unit. Now how far is it going to be drawn from the y-axis? 3 units. Its distance is getting stretched by 3. So it's going to end up plotted over here, and you can see how that would make your parabola go out more, and that's causing that horizontal stretch. Okay. All right, what is the other horizontal transformation here because h is equal to -3? Ethan? Good. So it shifted left 3 units. Okay. So not only are those distances going to change, but then the vertex is going to completely get moved to the left 3 units, and our parabola will be in a different position. Okay. All right, let's look at the vertical stuff. So we're looking now at the a value and the k value. Who can name for me one vertical transformation based on our a and our k value? Sammy. Okay, good. So we're going to shift up 5. So that takes care of the k value. All right, what else is going to happen to our graph based on the a value? Maddie? Okay, good. It's going to open down. And so how do we have to say that in now the correct vocab for our transformations? Peyton? Good. Okay, it's a reflection over. And if you have to pause for a minute, that's okay. Remember, if it's a vertical thing, it's changing the y's. But when you change a y from positive to negative, you flip it over the x-axis. Okay? What else? Yeah, Mary? Good. There's also a vertical stretch because a isn't just negative, it's a different number other than 1. So it is here. So again, I don't need you guys to go back and change yours. I just want you to understand what's happening visually here. So what's happening is these points are getting flipped over. Okay? Then they're getting stretched outward because of our horizontal stretch. Okay? But then they also have a vertical stretch. So they're also getting stretched further from the x-axis. Oops. And then the whole vertex of the parabola is in a different location, right? It was shifted, I don't know how far, I don't have my thing up here, let's see, to the left 3 and up 5. So it's going to be shaped like this, but to the left 3 and up 5 would put it here, and then I'd have that shape there. Does everybody kind of understand what's happening to it visually? So you can do the transformations visually if you want, but they take a lot of time and a lot of graphs. So there is a way for us to just transform the graph. When I was changing the horizontal stuff, okay, or let's do this, vertical stuff. When I flipped it over, what happened to the coordinates of the points? Like this point used to be at 1, 1, and now it's at what? It got flipped right here, reflected. What point is it at now? 1, -1. So if you had to say what was happening when a is negative, what do you do to what coordinate? The y coordinate gets multiplied by a negative, right? Is that okay with everybody? All right. Then you shift everything up 5. That was the other vertical thing. So it would be like up here. So now this point would be up here. So it was at 1, -1, and now it's going to be up here at 1, 4. What coordinate changed? The y coordinate. And what happened to it? It increased in value by exactly how much? 5. So if I want to reflect it, I just multiply it by a negative. You guys did this in geometry, right? With your transformations, they would have a little like mapping thing, like x + 1, y - 3, something like that. And you would change all the coordinates based on that. Essentially, we can do that too. So you have 2 options here. You can either take all those words and literally redraw the graph 5 times till you've gone through every transformation. Or you can say, you know what? I know the original points of the graph. When you square things, here's what happens to these numbers. And this is the parent function, right? Do you guys recognize this table? This is exactly what we did for the parent. I want to start with those points because those things are doing the squaring. They're taking part of what my math function I'm actually studying is, quadratic. Now that I've had all the squaring done, I just want to adjust the outcomes for the transformations. So horizontally, okay, we stretched by 3 and we shifted it to the left 5. So stretching things by 3 away from the x-axis means whatever their x-coordinate was before, you were 1 unit away, you now are 1 times 3, which is 3 units away. Is that okay with everybody? That's why I'm multiplying by 3. And then, oh, sorry, left 3. Sorry. And moving to the left 3. Is that okay with everybody? Sorry about that error. Then vertically, we're reflecting and we're stretching by 2. So we want all the y distances to double and then go in the other direction. And then we want to take the whole parabola and we want to move it up 5. So you can literally do this arithmetic on the numbers from your chart and it moves all the points to where they're supposed to be. Because when you were doing a vertical transformation, when you saw me just do that on the graph, the x's weren't changing, only the y's were changing, right? So when I want to change this 4, I take the 4 and multiply it by -2, that's -8. Then I add 5 to it and it becomes -3. And it would stay with the y or the x coordinate of -2 if there were no horizontal transformations. But we also had horizontal transformations, which means it's now not going to line up with an x of -2. It's going to line up at a new x value that's only affected by the horizontal stuff. Okay, so -2 would get multiplied by 3. That would be -6. Minus 3 would be -9. Okay. So we separately transform the original x coordinates to their new transformed values and the original y coordinates to their new transformed values because of how you saw me changing them before. When I was doing vertical things, it didn't affect the x. When I do horizontal things, it doesn't affect the y, so we treat them separately. But you have to know your parent function in order to do this. If you don't know your parent function, you don't have any starting point. Okay, and that can be memorizing it or quickly making it by just squaring those 5 key numbers. Okay, so I'm going to finish the chart. I'm now going to plug in -1 just to the horizontal transformation. So I'm going to stretch it by 3 and subtract 3. I'm going to plug in 0, stretch it by 3 and subtract 3, +1 and +2. And then I'm going to go through and do the vertical values. For them, I'm going to reflect them and stretch them by 2. So multiply by -2 and then add 5. So those end up looking like... Yes, Taylor. Because the a value was a 2. So the a has 2 things going on. The negative is causing the reflection. The 2 is causing a stretch, and we want to know exactly by how much. Okay? So if it was a 5 there, it would have been by 5. Katie? Is that okay? Yeah. Did you guys hear Katie's question? It was really good. Why did I write 3 times x when the b was 1/3? Because remember, the 1/3 in the equation means x takes, like, yes, it's going to take 3 times as long to get to the new y value. So remember, what it is in the equation means one thing, but we have to translate that to what it means on the graph. I am now going to plot these points, and I want you guys to look really carefully at the point in the middle of my table. This is really good for your arithmetic to check and see if you're doing it right. Notice that my vertex used to be at 0, 0 for the parent function. Where is my vertex now? -3, 5. Should it be at -3, 5? Yes. How do I know? Good, because my h is -3 and my k is 5. So I'm feeling pretty confident in the way that I've transformed my function. Okay, so I'm going to plot these points. And if it ever doesn't look like or your vertex doesn't match up, you just go back and you try again. Right. So again, if you don't like the plugging in points method, you can do, we used to make everyone do this. You can graph every transformation until you get the graph in the right place. But it takes like 6 graphs sometimes, okay, and it's pretty tedious. This makes it a little bit shorter and rearranges your points very quickly, just knowing the parent function really well, okay? And some checks at the end. Does your parabola face the way you expect it to face? Does it have the symmetry you expect it to have? Like, is there a clear axis of symmetry? Is the axis of symmetry in the right spot? And when I say the right spot, that means it would have the same x value as the vertex. And you should feel confident in your vertex because of the h and k values, all right? So this means that just by doing this, you guys can give me a table of values for this new function, and you can give me a graph of the new function fairly quickly. I know it's new, but we'll get better and better, and we're going to do this with every shape. So when we learn how to graph square root functions, we will do the exact same thing. What will be the only difference every time we learn a new function? What do you think would be different? Have the transformations changed? No, h and k do the same thing no matter what function we're studying. So if we were going to graph a square root, what would be the new piece of knowledge we would have to know? We already know how transformations work. The new parent function. That's it. So really, every time we learn a new function, we're learning a new visual with a new shape and a new set of like points that are the parent function. But all of this stuff here, the transformations, will be the same every single time. So if we can learn this well right now, we can understand when to stretch, when it's a compression, when we shift left and right and up and down. Those will serve you in every unit from here until we start trig second semester. In every single unit, we do at least one form of graphing a function. So we'll learn a new parent or two, but the transformations will stay the same. Is this okay with everybody? All right, and these transformations only work in this format, right? We've only studied like A, B, H, K when they're in these very specific places. So let's go through and let's kind of figure out the things down here. So new people, okay? Vertex, who can give me that? Peyton. Nice job. All right, we're gonna come back to x-intercept, okay? Talk about that in a minute, all right? Y-intercepts. Valerie. Good. And you guys could see it on the graph. If you couldn't see it on the graph, if it wasn't one of the points we plotted, how would you have found the y-intercept? Set what equal to 0? Here's set equal to 0. X, okay? So really you would have taken our equation, plugged 0 in for x, and you would have finished this arithmetic to get 3. The reason I'm pointing that out to you guys is a lot of you guys missed your y-intercept on your last one because you kind of just like estimated where it went, or your graph was wrong, so you put the wrong y-intercept. You should use algebra to check your graph. Like, this is not that complicated of a calculation. You can do it fairly quickly, and whatever you get here should match your graph, or you're either doing the calculation wrong or your graph was wrong. So it should serve as kind of a checking mechanism. All right, what about our domain? Someone new for this one. Yes, Vanna. Good job. So all real numbers, if we like interval notation, negative infinity to infinity. Our range. Yes, Sam.
Smaller than or equal to 5.
Good. Y is smaller than or equal to 5. If you like interval notation, that's no minimum with 5 as a maximum, and we reach 5. Increasing interval. Brody. Okay, really good idea. We just have to switch the 5 part of it, right? So it does go up to 5, but remember we want the notation to tell us the x value that it matches with when it switches. So instead of 5, you're right to use the vertex, but we want to use the x value of the vertex. So we want to say from negative infinity until, good, okay? All right, it does go up to 5, but you're not telling me what it goes up to. You're just telling me that on these x's it's behaving this way. All right, what about our decreasing interval? Angeline. Good. All right, is this function 1 to 1? No. Okay. And then we said rate of change we can't really identify now because it's different at each place. Somebody knew the axis of symmetry. Yeah, Hannah. Good, x equals -3. And you'll notice when you got your last test back, we are a little picky. If you just write -3, look at all the information you're writing here. Some things are points. Some things are numbers, some things are lines. If you don't tell me what it is, then I'm not just trying to be nitpicky. We literally don't know what -3 is. Is it a horizontal line? Is it a vertical line? Is it a value? You have to be a little more specific, okay? All right, somebody new, minimum value. Yari? None, good, okay. Maximum value, Valerie? Good. Okay, you can write 5 or y equals 5 for that one, that's fine. And then remember this function doesn't have asymptotes. Right. Other questions on what we did here. The characteristics I feel like you guys are fairly good with, but the graphing with the transformations part is kind of our new idea. Taylor? The b value? Okay. Yeah, so let's talk about the b value a little bit. So I'm going to go back to, I'll use x squared, the current function we're working with. And I'm just going to put part of the table here. And then what if I change it to this? Okay. If I put that portion of the table here now, 0 still becomes 0 squared. 1 now gets multiplied immediately by 2. So 1 times 2 is 2, and squared is 4. And then 2 gets multiplied by 2, that's 4, and squared is 16. So notice here that it took this much x's to reach a y value of 4. Is that okay? So it took 2 units horizontally to reach a y value of 4. This one also started at 0, 0, but how many units does it take to reach a y value of 4 here? Only 1 unit, right? Why that's happening is x is moving at double the speed, okay? It's going twice as fast because you're multiplying it by 2, so it's able to reach that y value twice as fast as it used to. But when we put it on the graph and we plot this, what that means is it used to take 2 units over to reach that value of 4, and that was that part of the parabola. But now, because it's going twice as fast, it reaches the y value faster, which means sooner, which means a smaller x value, not a bigger x value, okay? And when things move twice as fast, then distance-wise, which our graph is measuring distance, it takes half as long to get to the high point that you were at previously. So it used to take 2, but now it will take only 1. So a 2 in the equation means moving twice as fast, but on the graph that means I only need to travel half of the distance that I did before. Okay, so if the b value is 2, the compression on the graph is actually multiplying by the reciprocal of 2, which is 1/2. Okay, so using that logic, if I change this to something like 1/3, I would now say that x is moving 1/3 of the speed that it used to move. If I'm going 1/3 of my normal speed, I'm going to be slower or take longer to complete it. And how much longer is going to be 3 times longer because I'm only doing 1/3 of what I used to do in that distance. So in that case, you would multiply it by 3 and it would get stretched out further rather than closer. So for the b value, you're always going to use the reciprocal. So when I see 1/3, I know that I'm going to use 3. And if I'm using 3 on the graph, multiplying things by 3 makes them further away, which is a stretch rather than a compression. Is that okay? All right. Any other questions that you guys have? Okay, so go back now and do what I said is the regular algebra 2 problem that we didn't do. Okay, yes? Oh yeah, the x-intercept. Okay, so yes and no. We're actually going to do this a lot later in our class, but a small reminder right now, I guess we can do it. So this x doesn't cross at a clear place on this graph, but it does have x-intercepts. So algebraically, I'm setting y equal to 0. And I need to solve this for x. So there were problems kind of similar to this on your last weekly review, just easier. It didn't have like the 2 and the 5 here. What would I do to start solving this equation? Okay, I'm with you. I'm going to subtract 5. So I'm going to get -5 equals -2 times 1/3 x plus 1 squared. And if I take that route, what would be the next move that I'd want to make? Divide by 2. So I have 5 over 2 equals 1/3 x plus 1 squared. And what do I do at this point? Square root it, yeah. So some of you want to multiply it out. You can. And if you multiply it out, you're going to get it into standard form instead of vertex form. And then you're going to need to solve using the quadratic formula. If it's already in vertex form, you can solve by getting the squared part alone and taking square roots. What is a key thing you have to remember if you're square rooting both sides of the equation? Yeah, that there's a positive and a negative option here. If I say I'm thinking of a number and when you square it, you get 4. What's my number? 2 or negative 2. There's 2 possibilities. You need to explain that. This was that something squared became this positive 5 over 2. It could have been a negative number that was squared or a positive number. And this number is super ugly. And we just have to deal with that in this class, okay? So first, we don't really want a radical in the denominator. You can choose to deal with that now or later. I'm going to deal with it right now. So I'm going to multiply top and bottom by rad 2, because then my denominator is the square root of 2 times another square root of 2, which is actually equal to 2. All right, what do I do next? I'm just trying to get x alone. What do you need to do here to get x alone? Subtract 1. So you have a negative 1, and it can be both added or subtracted with this rad 10 over 2. And then what's the last thing I have to do to get x alone? Times it by 3. Okay, and it would distribute to this quantity since there's 2 terms. So those are my x-intercepts. So how we would write them as a point is that's how we'd write them. That would be the x. 3 rad 10 over 2, 0. With a y-coordinate of 0. How many x-intercepts is that? 2. Because the negative 3 can be added with that weird fraction, or the negative 3 could be subtracted with that fraction. So it would give me 2 values. I can get decimal approximations, but rad 10 is irrational, never-ending, non-repeating decimal. So if you write the decimal down, you actually do not have an exact answer. So fair warning in our course, if we're asking you for exact answers, that actually means just leave it with the rad 10 in it. That's the most exact way to write it. If you write it as a decimal, you're not going to write a never-ending decimal. How would you ever stop writing, right? So anywhere you stop is approximate because it didn't finish the rest of it. So the only way to write rad 10 without rounding or approximating is to literally leave it as rad 10. Is that okay with everybody? All right. Okay, go back and do the Algebra 2 one in your groups. So the other one on